All right, so this is where I stopped last week. So, what we were doing is we were finding um, how Kp is related to Kc. So, Kc is equilibrium constant and in terms of concentration, but there is another equilibrium constant in terms of partial pressure, which is called Kp. And we were trying to find a equation which shows relationship between Kp and Kc. Okay, so where to start off, we need to use the ideal gas law, which is PV equals nRT, and from here we rearranged this equation so that the P is equal to N over V RT. And then this N over V part, it's basically mole per liter, basically concentration of a substance. Okay, so now that we have, if we substitute this into here, we have this expression. Okay, so partial pressure of compound A equals to concentration of A times RT. R is a gas constant and T is a temperature. Okay, so now I'm going to show you the math how we got this equation where it shows relationship between Kp and Kc. I'm going to show you the math. You don't have to follow or memorize anything. You do have to follow, but you don't have to memorize anything because how we derive this equation is never going to be asked. So I'm just going to show you, take a brief note, and try to follow what I do. Okay. All right. So let's say you have an equation. Okay. So the capital letter A, B, C, D are the substances. So A and B are reactants, C and D are products. The smaller letter A, B, C, D indicates coefficients in front of them. Okay. So then this equation is what we already learned last week. Okay. So Kp, equilibrium constant in terms of pressure, is equal to partial pressure of compound D raised to its coefficient, power of its equal to its coefficient, partial pressure of E raised to the power equal to its coefficient. Same thing for compound A, same thing for compound B. Okay, so we do have this expression that we learned from last week, and now we have this information that we just obtained from here. Okay, partial pressure of A equals to concentration of A times RT. That means this equation applies to other compounds as well. So partial pressure of B is equal to concentration of B RT. Okay, so we know these informations. So what we're going to do is we're going to plug in this expression for PA this expression for PB, this expression for partial pressure. Oops, made a mistake here. This expression for, oops, C, D, for C, and then this for D, this. Okay, so then the Kp is going to be divided by okay. So I just replaced P to this, replaced PB to this, replaced PC to this, PD to this. That's all I did. Okay. So what we see from this equation is that we have a bunch of concentrations and we have a bunch of RTs. So let's rearrange this equation a little bit. If we put all the concentration on one side, we get and then if we put all the RT expressions on one side, we will have RT or okay. And these I'm not sure if you have already figured out, this is basically Kc. Concentration of products over concentration of reactants. Okay, so therefore Kp equals to Kc times RT coefficient C plus D minus coefficient A plus B. This coefficient is basically change in mole. Okay, this is basically change in the number of moles of gas in a balanced equation. Okay, so in order to calculate delta N, change in mole, what you have to do is you take mole of product minus mole of reactants. Okay, that's where you get the delta N. So instead of this long expression, let's replace this to delta N. Then we have Kp equals Kc RT delta N. Okay, this is how Kp and Kc are related. And this is how we arrive to this equation. Okay, so what this equation is telling us that if we know moles of product and reactants, if we know the reaction temperature, if we know Kc, we already know the gas constant, then we can easily find Kp value, vice versa. Okay, let's do a practice exercise. Okay, so for this Haber process, we are provided the mole information, the product, the reactant side has coefficient of 1 and 3, product has coefficient of 2. Okay, so using this information, we can easily find out the change in mole. Okay, we are provided with the Kc information, we're provided the temperature, we know the gas constant, so now we can easily find Kp using the equation that we just learned. Okay, so I'm going to write the equation first. Kp equals Kc times RT raised to the power of change in mole. Okay, so first, let's find the change in mole. Okay, change in number of mole of gas in balance equation, you have to add all the number of moles of the product. Okay, so 1 plus 3, this is 1 and 3, is 3, minus 2. Okay, these are the coefficients for reactants. Oh, I'm sorry. It should be product minus reactant. Mole of product is 2 minus sum of mole of reactant, 1 plus 3 equals to negative 2. Okay, so we have the delta N value. Another information that we're provided is Kc value 9.6. Temperature is 300 degrees Celsius, but the SI unit for temperature is Kelvin, so we are going to change into Kelvin, 573 Kelvin. Okay, gas constant, we already know 0.08206. You can find this value back of your textbook, or you can just Google it. Okay, so we all have all this information. We will just plug in these values to find the Kp. Okay, Kc is 9.60. Gas constant is 0.08206. Multiply by temperature 573 raised to the power of negative 2. This is 9.60 divided by okay. And by definition, rate constant is reported without the unit, so we're not going to worry about the unit when we work with Kp or Kc. Okay, so Kp equals to 4.34 times 10 to the negative 3. Okay.
Can you go back really quick, Professor?
Yeah, sure.
Professor, does Kp have any units that we should know about?
So by definition, equilibrium constants do not have units. So when you work with Kp or Kc, you have to report these values without the units. Okay, so even during the math, do not worry about the units because you're not going to report any units for these two constants. Okay.
Okay, thank you.
Mm-hmm. Let me know when you're done so I can move on to the next slide.
Go ahead.
All right. So now that we have finished exploring Kp, let's go back to Kc and discuss a little bit more about the equilibrium constant Kc. Okay. So again, Kc is a ratio of equilibrium concentration of product over concentration of reactant at equilibrium. Okay. So for an equilibrium reaction, for this equilibrium reaction, okay, where N2O4 dinitrogen tetroxide is decomposing into nitrogen dioxide, the ratio of concentration of product divided by concentration of reactant at equilibrium will be the same. Okay, so whether you start the reaction from the reactant side, whether you're starting the reaction from reactant side or product side, this is product side, the equilibrium concentration of reactant and product will be the ratio of equilibrium concentration of reactant and product will be the same. Okay, so this graph is showing that no matter what direction you start, you will have the same equilibrium concentration of NO2. Okay, so this blue line is showing that you're starting off with 0 NO2. Okay, so you're starting, the blue line is showing that you're starting with low concentration of NO2 or 0 concentration of NO2, 0 concentration of product. Experiment 3, here, you are starting with higher concentration of NO2. Okay, so no matter what direction you start your reaction, once you reach the equilibrium, your concentration of NO2 will be the same. Okay. This table summarizes experiment data from 4 different experiments, but the graph from previous slide was from experiment 3 and 4. Okay, so there are 2 things to note from this table. Number 1, as I mentioned from the previous slide, no matter what direction you start the reaction, once the equilibrium is reached, the ratio, the equilibrium constant, or the ratio of concentration of product over reactant at equilibrium is always the same. See, as you can see, whether you start with, for these 3 reactions, as you can see, you are starting with, I'm going to write the So for these 3 experiments, you're starting from 0 concentration of the reactant. So these 3 are talking about the reverse reaction. You're going from NO2 to N2O4. So it doesn't matter if you start your reaction from this side or this side, your Kc values are same or similar. Okay, so I'm going to summarize what I've just said. No matter what direction you start the reaction, the equilibrium constant, or Kc, always the same. Okay, and then second thing, a new thing to note from this table is that no matter what concentration of NO2 you begin with, although you will get different concentrations at equilibrium, the equilibrium constant or the ratio of this over this at equilibrium is the same. Okay, so if you started with low amount of NO2, you will have lower amount of N2O4 at equilibrium, and you will have lower amount of NO2 at equilibrium. However, the ratio is 0.211, and if you started with slightly higher amount of NO2, you will have slightly higher N2O4 at equilibrium. You will have slightly higher NO2 at equilibrium, but the ratio is same as when you started with lower amount of NO2. Okay. So that's the second thing to note. I'm going to summarize what I just said. No matter what concentration of NO2 you begin with, you'll get different concentrations of N2O4 and concentration of NO2 at equilibrium, but the Kc value is always the same. Okay, so these two are the two things that these two are the information that you can get from this table. It's all about the ratio. Okay. Let me know if I'm going too fast. Okay. So what does this magnitude of equilibrium constant Kc tell us? Okay. Since the magnitude of Kc is basically concentration of product over concentration of reactant at equilibrium, if K is a larger number, this means you have bigger number in the numerator, which means you have high concentration of product at equilibrium. So in this case, we say equilibrium lies to the right or product right side, or we say product predominates. Okay, so if K is large, that means you have a higher value in the numerator. That means you have higher concentration of product. That means the reaction favors products and product predominates at equilibrium. Okay. If K is a smaller number, that means you have smaller number in the numerator and you have bigger number in the denominator. Okay, this means that you have smaller concentration of product at equilibrium. Okay, and you have more reactant. In this case, we say equilibrium lies to the left side, or we say reactant predominate. Okay, so for reaction and reverse reaction, the rates are same, but the amount of concentration of product or reactants during the equilibrium state can vary. Okay, and that's what the magnitude of K tells us. Let's try a sample exercise. The following diagram represents 3 systems at equilibrium, okay? All in the same size containers. A, without doing any calculations, rank the systems in the order of increasing Kc. B, if the volume of the container is 1 liter and each sphere represents 0.1 mole, calculate Kc for each system. Okay, so for this question, let's do the question A first. For this question, we need to rank the systems in the order of increasing Kc. Okay, so smaller Kc to larger Kc. Smaller Kc, as we learned from the previous slide, smaller Kc represents smaller Kc means smaller concentration at equilibrium. Larger Kc represents higher concentration of product, right? Larger product concentration at equilibrium. Okay, so let's count the number of products in each box. Box one has 6 products. This is the product, and this is reactant. Box 1 has 1, 2, 3, 4, 5, 6 products. Okay, has 6 products, and box 2 has yellow is product, has 1 product. Box 3, red is product, 1, 2, 3, 4, 5, 6, 7, 8, 8 products. Okay. So product concentration is lowest in box 2. Then followed by box 1. And then box 3 has highest number of highest concentration of product. Okay, so therefore this rank is same as the Kc rank. So box 1 has smallest Kc, and then box 3 has largest Kc value because the concentration of product is increasing in this order. Okay. Moving on to question B. For this question, we need to calculate the exact numerical value of Kc. Okay. So they already provided us information that each sphere equals to 0.1 mole. Okay, and then it says the volume is 1 liter. Okay, so for then box 1, product for box 1 has 6 spheres. So 6 spheres equals to 0.6 mole. Okay. Since the volume is given that it's 1 liter, the concentration of product or concentration of product is going to be 0.6 mole per liter, which is 0.6 mole per liter. This is the concentration of product. Okay. As for the reactant, box 1 has 1, 2, 3, 4 reactants. Each sphere is equal to 0.1 mole, so if we do 4 times 0.1 mole, that equals to 0.4 mole. Okay, so the concentration of reactant is going to be 0.4 mole divided by 1 liter. That's 0.4 mole per liter. Okay, so now we have equilibrium concentration of product and reactant. Can we find Kc? Kc for box 1 is going to be concentration of product divided by concentration of reactant at equilibrium. So 0.6 divided by 0.4 equals to 1.5. Okay. So if you do the same thing for box 2 and box 4, you're going to find Kc value for box 2 is going to be 0.11. Box 3 is going to be 0.8 divided by 0.2 is 4.0. Okay. So remember how we ranked the Kc without doing any mathematical calculations. See if it matches with what we ranked. Okay, so indeed box 2 had smallest Kc value, then box 1 had slightly larger Kc value, and indeed box 3 had largest Kc value. Okay, so what we predicted here was correct. Okay, I'm not going to go over the detailed math for these parts because I'm running out of time. Okay. Does anybody need more time for this slide?
Yes, please.
Okay. Let me know when you're done.
Professor, one question. When we have our exam, will it be laid out like the notes or like the homework?
The format of the question?
Yeah.
It's going to be multiple choice.
Yeah, but should we expect it to be like the examples you're giving us, or should we focus more on the homework for our examples to practice?
I don't know what the difference is. 'Cause,
So basically, both the homework and the notes are the same, the examples you give us.
are you asking what type of question am I gonna put on the exam?
Yeah, basically, yeah.
Oh. I think it's going to be a mixture of both whatever is on the lecture note and the homework. It's going to be combination.
Okay.
Yeah.
Yeah, okay, thank you.
Mm-hmm. Okay. Can I move on to the next slide?
Yes, I just finished. Thank you.
Okay. All right. So what happens to the Kc when you're evaluating a reverse reaction? Okay. What is the equilibrium constant for reverse? Okay. So for this is the original equation that we have. Okay. And in the reverse reactions point of view, now for the original reaction, this is reactant, this is product. However, from the reverse reactions point of view, now the NO2 is no longer a product in the point of reverse reactions point of view. Now this is the reactant and this is the product. So what happens to the Kc is that Kc for reverse reaction would be concentration of N2O4 at equilibrium divided by concentration of NO2 raised to the power equal to the coefficient of the reactant. Okay. So the Kc for reverse reaction is basically the reciprocal of the Kc for the forward reaction. Okay. So it's basically 1 over 0.212 equals 4.72. Okay. So if you were given Kc for the forward reaction as a number, and if you were asked to find the Kc for the reverse reaction, all you have to do, you don't really have to do all these math. What you have to do is you simply take 1 divided by the Kc value of the forward reaction, and you will get the Kc value for the reverse reaction. Okay. And what would happen if you have an equation that has been multiplied by a number? Would Kc change? The answer is yes. So let's evaluate this equation. What if we multiply this equation by a number of 2? Then the coefficient is going to be 2 in front of N2O4, 2 times 2, the coefficient of NO2. To find the new equilibrium constant of a reaction when the equation has been multiplied by a number, simply raise the original equilibrium constant to that power. Okay, so here the stoichiometry is doubled, right? It's doubled. So the below reaction is basically the above reaction multiplied by 2. So then the equilibrium constant for the new reaction is squared. Is raised to the power equal to the whatever number that has been multiplied to the new equation. If the new equation is multiplied by 3, then you will have this, and then the Kc is going to be basically original equation raised to the power of 3. Okay. So in the exam or homework assignment, if you see a new reaction where it has been multiplied by a number from the original reaction, don't forget to raise the equilibrium constant to the power of the number that has been multiplied to the new reaction. Okay. So to and then and here's another situation. Here's a situation where you know the equilibrium constant for each elementary steps, and you have to find the overall reaction to equilibrium constant. Okay, so if each elementary reaction to equilibrium constants are given, the overall reaction to equilibrium constant, or you can call it combined equilibrium constant, is basically product of the equilibrium constant for each individual reactions in the elementary steps. So for example, if this elementary step has Kc value of 0.014, the one okay? If this elementary this
Professor, I don't know if it's my internet, but you're breaking off.
okay, then the combined
Professor, you're breaking out.
reactions Kc, I'm breaking out. Okay. That's weird. Is it better now? Or am I still breaking out?
It's better now.
Okay. All right. Okay. So let me repeat what I've just said. These are the elementary reactions. Sorry, my Apple Pencil is not working. It's weird. Okay, it's working now. Oh, what's going on? Okay, my Apple Pencil is not working. All right. Let me try GoodNote. Okay. All right. Oh, I think my iPad is having having a problem. One second, Glory. 1 second. I'm going. Okay, I think I fixed it. I'm going to use a GoodNote instead of the Notability. See if this works. All right, so one and two should be the slide. Yeah, I think my iPad is having.
Yeah, I know. That's why I was kind of like, and like she was like I guess the county doctors were like calling her and like asking her because now there's like since your kids are missing on volleyball tryouts, how parents get. They're like getting all pissed and they're calling the county and saying that we said the wrong things and now their kids can't make the team.
Hey Tatiana, your speaker's on.
Sorry about this. I don't know what's going on today. Oh. Okay. What is going on? All right, can you guys see this screen?
Yes.
Okay. So since Notability and GoodNote are both not working, I'm not going to be able to use my Apple Pencil. So I'm just going to explain the best I can. Okay. So anyways, we were looking at situation where two elementary reactions combine to form one overall reaction. Okay, so here's the NOBR going to NO and BR2. This is the one elementary reaction. Okay, we're going to label it as reaction 1, which has a rate constant of 0.014. Okay, because this is a reaction number 1, we label it as K1. Okay, second elementary reaction is Br2 plus Cl2, also a reversible reaction, but the product is 2BrCl. Okay, this second elementary reaction is rate constant is labeled as K2, and it has a value of 7.2. Okay, so the overall reaction is going to be combination of elementary reaction 1, elementary reaction 2, which is 2NOBr plus Cl2 producing NO, 2NO plus 2BrCl. So this is a combined reaction of two elementary reactions. Okay, so the overall reaction's equilibrium constant is labeled as K3. Okay, or you can just put K, you can label whatever the way you want. Okay, but K3 here is indicating the overall reaction's equilibrium constant. Okay, when you are finding overall reactions equilibrium constant, all you have to do is you have to multiply equilibrium constant of each elementary steps. Okay, so elementary step 1 had equilibrium constant of 0.014, so we put 0.014 for the first reaction's equilibrium constant. Elementary reaction 2 had rate constant, equilibrium constant of 7.2, so we put 7.2 as for the equilibrium constant for the second elementary reaction. Okay, product of these two values. If you multiply equilibrium constant of two elementary steps, you will get the overall reaction's equilibrium constant. Okay, you basically have to multiply two values. Okay, since I'm not able to use the Apple Pencil, I'm going to save this for next class. Okay. Let's take a look at the homogeneous and heterogeneous equilibria. Okay, homogeneous equilibria is when all reactants and products are in the same phase. Okay, heterogeneous equilibria is when something is in the equilibrium is in different phase. Okay, so let me try one more time. Equilibria, okay, where all the substance participating in the reaction are in the same state. They're both in gas state. The reactant is in gas state, the product is in gas state. Example of heterogeneous equilibria would be something like this, okay, where calcium carbonate is in solid state, producing calcium oxide in solid state, plus carbon dioxide in gas state. You have two substances in solid state and one substance in gas state. Okay, so when the substance within the reaction, they're in different phase, we call this heterogeneous equilibria. Okay, is my screen looking okay to you guys?
Yes.
Okay, all right, so if you look over here, we're dealing with solids. Okay, let's say we are dealing with a chemical reaction that involves pure solid. Okay, or we're dealing with pure liquid. Example will be lead, solid, or water, liquid. Pure solid and pure liquid, should we include these substances in the equilibrium expression? The answer is no. Okay, while equilibrium constant expression includes terms only for reactants and products whose concentration can change or can vary during the reaction, the concentration of these pure solid and pure liquid do not fluctuate. Concentrations of these do not fluctuate. Okay? Therefore, we cannot change their concentration. Concentration of water, you cannot dilute water or you cannot make water more concentrated. Okay? Water will have a density of 1 no matter what. So therefore, pure solids and pure liquids, you cannot dilute them or you cannot make them more concentrated. And because we cannot change, we cannot vary their concentrations, we don't want to include them in the equilibrium constant expression. Okay, so whenever you see pure solid and pure liquid in the equation, okay, you want to exclude them from the equilibrium constant expression. Okay, or you can think of these value as 1. Okay, let's take a look at the example. Okay. I hope the screen is looking okay. If it's frozen or if it's not looking clearly, let me know ASAP, please. Okay. So here is this is heterogeneous example of heterogeneous equilibrium where you have you're seeing the decomposition of calcium carbonate into calcium oxide and calcium carbon dioxide. Okay. So in order to express this equilibrium constant, you would omit these solid concentrations. Okay, so the equilibrium constant Kc value for this reaction would only contain concentration of carbon dioxide at equilibrium only. Okay.
Professor,
Yeah.
since Kc is product over reactants, wouldn't Kc be 1 over CO2?
Product. CO2 is product. CO2 is product.
Oh,
right?
that's right.
But
Yes, that's right. Sorry, thank you.
Uh-huh. Okay. So as you can see from the diagram, here, the constant, here's a solid powder. I don't want to zoom in because I don't want to freeze the screen, but here's a solid powder of calcium carbonate, solid powder of calcium oxide, also calcium carbonate, calcium oxide. Their amount varies. However, their concentration do not fluctuate. Calcium carbonate will have same concentration no matter what. Calcium oxide will have same concentration no matter what. Okay, so the concentrations for these solids and pure solids and pure liquids, they do not vary with the amount. Okay, so therefore they have flat concentrations. Okay. All right, so as you can see from the diagram, regardless of the amount of solid substances, you have equal amount of carbon dioxide at equilibrium. Okay, I'm going to write that down. Regardless of the amount of substances, I'm talking about solid, pure solid substances, you have equal amount of carbon dioxide at equilibrium. Okay, so again, don't forget to exclude pure solid and pure liquids concentration in the equilibrium constant expression. Okay, all right. Let's try a sample exercise. We write the equilibrium constant expression for Kc. Okay, very simple. For A, we have pure liquid, which is water. We're going to exclude this from the equilibrium constant expression. So the Kc is going to be something like this. For B, we have solid on this side, solid on this side, okay? Which we're going to exclude. So the Kc is going to be CO2 raised to the power equal to the coefficient divided by CO raised to the power equal to the coefficient. All right. Can I move on?
Yes.
Okay. All right, next exercise. So now we have explored further details about Kc. Let's quickly go back to Kp, see if you can remember what Kp is. Okay, so Kp was the equilibrium constant in terms of partial pressure, right? So in the previous exercise, the only type of exercise we've done was to calculate Kp from Kc or Kc from Kp, right? In this exercise, they provide you with the numerical values of partial pressures of each reactants and product. Okay. Again, so let's read the question. After a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius, it is found to contain 7.38 atm. Atm is unit for partial pressure. Okay. 2.46 atm of nitrogen and 0.166 atm of NH3. Okay, from these data, calculate the equilibrium constant Kp for the reaction. Okay, since atm is unit of partial pressure, and since the partial pressure values are given, you just have to plug these values into the Kp equation to find the Kp. Okay, so similar to when we calculate Kc, the Kp is going to be partial pressure of the product raised to the power equal to its coefficient divided by partial pressure of reactants, each raised to the power equal to the coefficients, right? So P NH3 raised to the second power divided by, Pn2 times pH2 raised to the third power. Okay, so we just have to plug in all the values that they provided. 0.166 square divided by 2.46, 7.38, power of 3 equals to 2.79 times 10 to the negative 5. Kp and Kc are rate constants. By definition, we don't put unit. They don't have units. Okay, so do not worry about units. All right. We're going to move on to another practice situation where we are only provided with initial concentrations. Okay, and we only know some of the concentration of substances at equilibrium. Okay, these are the steps that you would follow, but it will be hard to understand these sentences right now. So we're going to take a look at the specific example, and we're going to come back to this slide. So this slide is a summary of what we're going to be doing in next few slides. Okay, so we're going to come back to this slide. Okay, so this is a practice situation where initial concentration of two reactants are given. Okay, initially containing, this is the concentration of first reactant, and this is the concentration of second reactant. Okay, and as you know, initial concentrations cannot be used toward equilibrium constant calculation. Initial concentrations cannot be used toward equilibrium constant calculations. Okay, the only concentration at equilibrium provided here is the products. It says equilibrium mixture shows the concentration of product to be this. So the only concentration at equilibrium provided here is the product's concentration. Okay, so the approach is we will use product's concentration at equilibrium to find reactants concentration at equilibrium. Once we have all of the reactants and products concentration at equilibrium, then we can use those concentration values to calculate the equilibrium constant C. Okay, so I'm going to write down the approach or plan. Okay, we need to find concentrations of all reactants and product at equilibrium. Then we can use those concentrations to find equilibrium constant Kc. Okay. So again, to summarize the situation here, we're provided initial concentrations of two of the reactants, and we're only provided equilibrium concentration of the product. Okay, they want you to find the Kc. However, without the equal concentrations of reactants at equilibrium, we cannot find Kc. Okay, so we're going to find concentrations of all the reactants at equilibrium. Product equilibrium concentration we already know. So once we have all the concentration of reactants and products at equilibrium, then we will use those concentration values to find the equilibrium constant Kc. Okay, so the takeaway is initial concentration, you cannot use these concentrations toward equilibrium constant calculations. Okay, we're running out of time, so I'm going to continue next class. I'm going to hang out for another 5 to 10 minutes just in case anybody else has questions. I apologize for all the technical issues today. I don't know what's going on with my iPad. I'll try to figure it out by Thursday. Hopefully it doesn't happen on Thursday. If you don't have any questions, you can exit the meeting and I will see you again on Thursday. Okay?
Professor, one question.
Yeah.
So for some reason, my computer deleted my notes from last class. I don't know if you would be posting these notes.
Yeah, so
Okay.
so many of you guys are requesting. I will post the lecture notes with my handwriting on it, but I'm going to post once I finish the entire chapter. Is that
Okay, yeah.
So,
Yeah, that
for
works.
chapter, are you talking about chapter 14 or chapter 15?
15.
15. Okay, 15. Then you might want to wait until Thursday afternoon. Yeah, because by Thursday we're gonna finish chapter 15, and then I'm going to upload the lecture note with my handwriting that night.
Okay. Thank you so much.
Mm-hmm.